Hi, good morning, students. This is our chapter 4. We already done with the discrete probability random variables and their distributions. In chapter 4 here, we study the continuous random variables and their distributions, which we will have to study the same points we studied before, how to define the probability function and how to calculate a probability, and then how to calculate the CDF or the distribution function of the random variable in hand, and how to get the expected value and the variance. Also, we have to study the moment generating function as we did in the previous chapter, chapter 3. In this chapter, we will do it on two parts. The first part will be how to define the continuous random variables and what is or what are the differences between the discrete and continuous random variables, and also what is the difference in defining the probability distribution of the continuous random variable here, which is the second point before us, called probability density function. Third, we'll study how to obtain the distribution function or cumulative distribution function CDF. This is in the first part, as will be done here. The second part will be the last 3 points: expectation and variance, moments, and moment generating function. So here we start with the first point, which is what is the difference between the continuous random variables and the discrete random variables from the definition point of view. The discrete random variables, like as we see before us here in this slide, like the number of books, which we call it a discrete random variable, can take it's either 0 or 1 or 2 or 3 and so on. So 0, it means that you don't have any books. 1, you have 1 book, or 2 boxes, or 3 dots. So this random variable take jump points. It's either 0, then jump to 1, then jump to 2, then jump to 3, up to the maximum number of points you have, or maximum number of books you have. But for the continuous case, like the oil price, this one I cannot determine a specific value. All what I can say is that the oil price is between 34 and 34.5. So the oil price can be any value with any decimal points number in between. So look at the difference here. The discrete case, the number of books take one specific value equal to 3. Here, the continuous case, the oil price can take an interval from 34 to 34.5 with any possible value in between. So here we have some examples for the continuous random variables. As you see here written in red, our continuous random variable may be the temperature, maybe the computer time, maybe the lifetime of a bulb, maybe the waiting time until you get your service done, maybe the height of an individual, maybe the age of patients with a certain illness. And please again, we need here to emphasize on the fact that any of these variables cannot take equal a specific value. It has to be an interval. Let me give you an example which is very important for you to understand this case. Like the last case, the age. If I'm talking about my age, and suppose I am born in the same day, in the same second, in the same minute, exactly 50 years back, and somebody's asking me, why is the age for Abdel Nasser? So can we say that the age of Abdel Nasser Y equal 50? This is not true, because whenever you say the age, whenever you just say my age, there is another second passed by. So your age cannot be determined exactly to the minute and the second and sub-seconds. You can truly say that my age is between 50 and 2 hours. This is okay if you are even born in the same minute like 50 years back. The same for height. If you are talking about your height, you cannot say my height is 161.5, because if the scale is very accurate, you need to say what are the decimal points of the scale over the 160.5 or 61.5 or something like that. The decimal points more than that, the scale can only give you up to 0.5, but there is more. Also the weight. If you have a scale and you are weighting yourself, you cannot say that it's exactly, my weight is exactly 55.3. There is some grams and some fractions of the grams, but the scale does not give you this. So it's truly, actually, we can say it's between 53.2 and 53.3, say, or 53.2 and 53.5. So it's an interval for the continuous case. We cannot put it equal a specific number, only because of our tools cannot give me the exact number with all decimal points required. Here you can see more examples for the daily rain and the waiting time for a specific customer to spend online at store. Just more examples to see that the amount of rain and the waiting times are examples of continuous random variables, which we have to talk about these variables in terms of intervals between two values. It cannot take a specific value. So since our continuous random variable like age or price or weight or height cannot take a specific value, we cannot do like the discrete random variable and assign a probability for the value, because there is no value here. Value in discrete, but here we talk about interval. So we cannot see like a table or something like in the discrete case a value and probability. No, here we talk about interval, and we have to get the probability of the continuous random variable in an interval not equal to a value. If somebody asks you what is the probability that the time until a specific service will be done equal to 10 minutes, you have to say the chance for that, the probability for that is 0. So your continuous random variable is defined to be interval, not a value. The chance to take a specific value is 0, as you will see in the next few slides. Now, how we define the probability on the continuous case, you will see that we have to have what we call the probability density function. Go back and remember that in the discrete case, it was the probability mass function, PMF, probability mass function, like the binomial case, a function or a formula that you plug in the value like 0 or 1, you get a probability. Here, we have to define a new function, which is a continuous function, which can give me the probability of a random variable in an interval. This function, we call it a probability density function, or PDF. In this slide and the next one, you can see some explanations of the relation between discrete and continuous. Whenever the discrete random variable can come closer to each other, so that you dissect the distance between the discrete value of the random variables more often, and they get so close to each other, we move to the continuous case. So just read this slide with the example of the depth of the water and the next one to see how this one can relate to the previous discrete one. So now how to get the probability of a continuous random variable? Again, let me emphasize before we do this, the probability that y is a continuous random variable now, to take a specific value c equal to 0. So no continuous random variable can assign a specific value, it has to be an interval. Now, we said that the random variable, which is a continuous one, works in an interval. How we calculate the probability? So we have to get an area under a curve. So the probability from now on, which is the probability of y, which is like time between 10 minutes and 15 minutes, is an area under the curve, which we called it probability density function. So we'll have a probability density function, which is a continuous curve if you graph it. In order to get a specific probability between 2 points like an interval, you have to calculate the area under this curve or under the probability density function. So probability area, please remember probability area, and even it gives you the meaning for the probability at a value equals 0. If you recognize, if you always associate that the probability on continuous case, time, age, and so on, a probability for an interval, it's an area. So can you get an area at a specific point? No. In order to get an area, to get a probability, I need two vertical lines to get an area in between them and the curve. But to get an area at a specific point, there is no area at a specific point. The area here at a specific point will be 0. So the probability that y equals c is 0. And in order to calculate the probability from now on, since an area under a curve, we have to work with the definite integration, which is an integration as you studied in calculus, that works between two values. So we integrate under an interval from a to b under the curve, which is, we call it the probability density function, dx or dy, to calculate the required probability as an area. So again here, as we continue, we say that our y works in an interval a and b, so my y works between a and b, and in order to calculate its probability, the probability that y is between the value a and the value b, b is greater than a, is the integration under the probability density function f of y dy from a to b. If you remember, we're supposed to integrate the function that it will be given, then substitute the upper bound b minus substituting inside the integration the value a, as we'll see later on. So from now on, this is important remark here. The probability that y between a and b without writing equal, so a less than y less than b, is exactly the same like if you say the probability y greater than or equal a less than b, or even if you put the equal at b only, or if you put the equal at a and b. Why these are all equal? Because at the point itself, if you write the equal at a or at b or at both, at the point itself, there is no probability. The probability in between the A and B, not exactly at the point itself. So please take care, because I can ask you, like the probability y between A and B without equal, or with only one direction equal in A or in B or in both, all these are the same. You just have to do the integration from A to B under the density function f of y dy to calculate the probability, whatever the form with equal or not equal written to you. So here, like the one we studied in the discrete case, what is the probability density function, or PDF? The PDF is just a a continuous function that you need to use in order to integrate or calculate the probability for the random variable you are talking about y, but it has to have the two following conditions. The first one is that the density function, the function itself is above the horizontal line, so it's a positive, or minimum it will be zero. It cannot cross the horizontal line. It has to be always positive for all values of y, or at least zero. The second condition, if you remember from the discrete point of view, the sum of the probabilities for the whole table of probability distribution is 1. Here, the total integration under the whole curve from the beginning of the values of y up to the end has to add up to 1, and this is your check that you have a probability density function like the one in the table. The sum of the total probabilities is 1. Here the integration, which is the total probability by integration for the whole values of y, has to be 1. Now, since we need to integrate under the probability density function to obtain a required probability for y, which is a continuous random variable, we need to remember the integration rules or formulas, which are very simple. As you see here, we will not go through the hard ones or the complicated ones. The first rule, as you see, if you are integrating a constant a like 5, so your integration will be 5x plus c. If you integrate x with a power like n, increase the power by 1, so it will be x power n plus 1 and divide by the new power plus c. If you are integrating, like in rule number 3, e to the power ax, you just have to put the function as it is, e to the power ax over a plus c. Like in number 4, if you are integrating 1 over x, you need to write it's ln x plus c. If you are integrating like a rule 5, a constant multiply by x's, f of x, any x's, you get the constant out, which is k, then you integrate the x's. Last rule, if you are integrating a function of x's plus or minus another function of x's, you can integrate each part separately. Like you put the integration for each part and integrate it separately, then you plus the answer from here, or you minus the answer from here with the minus from here. But this is not true. Rule number 6 is not true if you have a multiplication or division. If you have a multiplication or division, you cannot integrate each part multiplied and then you multiply, or each of your numerator separately and denominator separately and then divide. This is wrong in the case of multiplication and division. You can always use it in plus and minus. Do each part, then plus and minus, but not in our integration. As we said, to calculate a probability, we need to use definite integrals, not like the previous rules. The previous rules, there is no limits over the integral, so we add up c. But here, if we need to calculate a probability, which is an area under a curve between a and b, like the problem before us, integration from a to b 3x dx, you get the 3 out, and then you integrate from a to b x dx, which is like x power 1. We increase the power by 1, it will be x squared over 2. Then we substitute, replacing x by b, minus we substitute x by a. As we see before us, it will be 3 open bracket b squared over 2 minus a squared over 2, and this is our answer. I just got this example to tell you that in our calculation of probability, you apply the rule, but you do not add up C. There is no C's in calculating areas or probabilities. Okay? Now this is our first example for the continuous random variable, and as you see here, he gave us the probability density function for the random variable y as the cy squared when your variable y works from 0 to 2 and 0 elsewhere. And the first requirement he is asking us to get is the value of c in the density function such that your density here, such that your probability function here is a valid one. Now, in order to do this, we use the property for the probability distribution, generally whatever it's discrete or continuous, using different means, that the total probability is supposed to be 1. In our discrete case, we sum the total probability in the table of probabilities or the probability distribution, we get it 1. Here, we integrate the total area under what we call the density function or the probability density function curve, and it has to be 1. And this is easy to do, since if you integrate from the values or over the values of your variable from 0 up to 2, we can get the value c by equating this integration to 1. As you see here, the integration of cy squared dy is you put the c aside, and the integration of y squared is y cubed over 3. Then we substitute by 2, replacing the y by 2. We have c 2 cubed over 3 minus, you substitute the lower bound, which is 0, c 0 power 3 over 3. So we get the value as you see here, which is 8 over 3c. Now, if we equate this with 1, we get the, as here, you can see that we get the c equal 3 over 8. Our second question now is number 2. Find the probability that y between 1 and 2, there is an equal sign in the direction of 1 and in the direction of 2. But you can see that this is the same if you say the remaining part of the question, also find the probability that y between 1 and 2, because you put equal in the side of 1 or in the direction of 2, it does not make any difference, because as we said earlier, the probability at the same point, exactly at the point 1 or at the point 2, is 0. So all what we have to do now to calculate the probability that y between 1 and 2 is to integrate from 1 to 2 over the density function he gave us, which is f of y dy, which is 3 over 8, replacing the c by 3 over 8 y squared in order to get the probability, which, as we did before, y squared, it will be y cubed over 3. Then we substitute the y one time with 2 minus another time we substitute the y by 1. We get the value of the probability required in number 2 as 7 over 8. And this completes the problem number 1. Here is another example for the calculation of probabilities or finding the constants for our probability density function in the continuous random variable case. So here, as you see, again, he gave us the density function for the random variable as the f of y equals cy cubed multiplied by 1 minus y. If you notice that the function has a y cubed multiplied by 1 minus y. So in order to simplify before you do anything, the best thing is that you multiply the y cubed by the inside bracket. So it will be y cubed by 1, it will be y cubed multiplied by y, it will be y power 4. Before you start do anything, because as we said earlier, you cannot integrate a multiplication. You have to multiply and make it a term of y minus or plus another term of y. So here again, he's asking us in the first requirement to obtain the value of C such that your probability density function is a proper one or a valid one. And again, as we did before, we can only apply the rule that the total area under the curve or the total integration equal to 1. And again, since our variable works only from 0 to 1, we can integrate here from 0 to 1 over the density function after simplifying, as we said. So as you remember, it's a C multiplied by y cubed minus y power 4. So the integration of y cubed after you simplify it will be y power 4 over 4, and the y power 4 it will be y power 5 over 5. Then we substitute by 1 replacing the y's, minus you substitute each y by 0, you get this C multiplied by 1 over 20. If you equate this with 1, you get your C equal to 20. In the second requirement, or requirement number 2, he is asking the probability that y less than or equal a half, as you see here. In order to get this, we need to do an integration. And to get y less than or equal a half, we need to integrate from the starting point of your variable, which is 0, up to the value you need, which is half, as he asked y less than or equal a half, over the density function you have. Again, like what we did to get the C, we can integrate the y cubed multiplied inside the bracket first, then integrate the y cubed into y power 4 over 4, the y power 4 into y power 5 over 5, then substitute by, one time you substitute by half, another time you replace each y by 0, which will cancel because when you substitute y by zeros, it will give you the 0. Then you obtain the probability required, which is 3 over 16. The second part of the requirement here, which is probability that y is greater or equal half, this is the complement of the first one. Remember, in the first part, we get y less than or equal half. So if we need the probability of y greater than or equal half, all what we have to do, like here, to get 1 minus the probability we obtain in step number 2, we can get the required probability as 3 over 16, because these two events are complementing each other to 1. So this is a second example which give you again the chance to calculate C and to calculate a specific probability, and also use the complement rule. Now this is our third example, which he gave us the density function or the PDF as C over root y, and you remember, and your y works from 0 to 1, but you remember, in order to integrate something like a fraction, we cannot do an integration for the numerator separately and the denominator separately. We can just put y here, which is the root of y, we can put it in the numerator as y to the power negative half, because the root is y power half, and if we move it up, we can just say it's y power negative half. Then we can do our integration very easily as we did before. As you see down here, equating the integration by 1, finally, we can get the C. You see that the integration of y power negative half, if you increase the power, which is negative half, by 1, it will be y power half. Then you divide by the new power, which now is half. Then substitute one time y equals 1, another time minus, you substitute y equals 0. You can obtain the C exactly like the way we did before. All in what happened in this problem that it was a fraction and I cannot integrate the fraction as a numerator and denominator each one separately. I have to manipulate the problem to make my denominator as a numerator because the variable in my denominator so that I can do the integration in the numerator and finish the substitution and get the value of C. Now we are done with the first point, which is the continuous random variables. And you saw this one we compare with the discrete to tell you that the continuous random variable is defined as a variable in an interval. Then the second one, which is the probability density function, the function that looks like a curve, and we get the probability calculation as an integration under the curve according to the question from where to where or less than what or greater than what you need the probability for. Now we will go to the third point here, which is the cumulative distribution function, or we call it CDF or DF for short. This one we did it in the table by doing a very large curly bracket. If you remember, starting with the 0 and end up with 1. You will see also that we can do this here, but instead of summing probabilities like in the discrete, we integrate in order to get the required probability as the coming few slides. So to remind you again with what is the distribution function is, this is the definition of the CDF or the distribution function of a random variable. We write it a capital F, but the definition is that the probability that y is less than or equal a value. The value here is a small y. In the discrete, we call it k or t. It doesn't matter. It's the probability that your variable is less than a specific given value. So our capital F here is used or defined by this definition. And this, since we are talking about curve, we will have to get it using integrations because you need from a specific value as we see on the graph here up to the value we need to get the probability from this value down. So the area to the left of the y naught or small y as you see in your picture here. The same if the curve is different, like for example this curve, we can see also if you need from 8 down, we need the area shaded to the left of 8, from 8 up to the starting point where the curve starts, which is 5, and this to be considered f of 8 because y less than or equal to 8. Now let us remember as before that our capital F of y is a continuous function, and we said that this function represents the probability that y less than or equal a value. So whenever this function is defined, we can define the probability density function that we have. As we'll see in the coming few slides, if we know the capital F, we can get the small f, which is the density function. And if I have the density function by integration, I can get the capital F, which is the distribution function here. Now, these are the properties which we mentioned in the study of the distribution function when we studied the discrete random variable, is that the distribution function, the minimum point is 0, and the maximum point in the curly bracket, it was 1. So this is the smallest and the largest value for f. We get the 0 if you put the minimum value for y, because if you have the minimum value for y, for example, is 5. what is the probability that your y less than or equal 5? There is no probability less than or equal 5. My starting point is 5. So I don't have any probabilities less than that. And if you put the highest value for your variable y, you can get the capital F as 1 because you add up all probabilities under the maximum value you have for your variable, so it will give you 1. Again, if you remember from the definition of the capital F, if you need the probability that your y is between A and B, all what I can do is that to substitute in my capital F with B, the upper limit, minus to substitute in my capital F with A, I will get the probability because the capital F of B is the probability less than or equal to B, and the probability, the capital F at A is less than or equal to A. So if you subtract, it will give you the probability that your Y in between, as I'm trying to show you here with my handwriting graph. It's a bad, but if you get a capital F at B in the beginning, you get the whole of these probabilities down. And then when you subtract from it the capital F at A, you subtract this area, so you have the difference between them as the area from B up to this point only, which is, I'm trying to shade it before you now. This is an example that he gave us the probability density function for the random variable y as you see before you here, it's 3y squared when your y works between 0 and 1. And if your y is outside this range, it means under 0 or over 1, the function itself disappear or vanish, it's 0. And the first question here is that he asks for the distribution function or the CDF. Then we need to graph the function given, which is the probability density function, and the capital F, which is the distribution function. To start our solution, we can remember that when you want to get the capital F for the any random variable, we start by a large curly bracket, and then we have two sides. It's either the left hand side here or the right hand side, which is here. And we always start by writing the right hand side. And we said if your variable as above starts from 0 to 1, we start our y before the range, before 0, in the middle of the range, in the middle between 0 and 1, then over the range if my y is greater than 1. And mechanically speaking, you know that when you start before the range in the first branch, your capital F has to equal to 0. And also, if you start over the range, your capital F has to be 1. You can just write them and you are done with these two branches. The only branch you need to take care of is the branch when you put your y in the middle of 0 and 1 here, because you have to integrate over the function he gave you from the starting point in your range, which is 0, up to a value called y. The y here can represent any value. So we are integrating from 0 to y, the function he gave us, which is 3t squared or 3y squared. It doesn't matter, you call it 3t squared or 3y squared. And the integration of 3t squared is t cubed. Then you substitute, replacing the t by y, and replacing minus, you replace it by 0, so you get y cubed as a final solution. So our curly bracket have a 0 in the first branch, have a y cubed in the second branch, have 1 in the third branch. So we got the capital F or the distribution function. In order to graph them, it's easy. Generally speaking, if I give you a function, in order to graph it, just look at the boundaries. Our boundaries for the small f, which he gave us, is the y works from 0 to 1. So you graph your axis, the y-axis, which is the horizontal one, and f of y, which is the vertical one, then you can graph only the function in these two parts, which is from 0 to 1, by looking at the original function, which is 3y squared, substituting the first value of your y, which is 0, it will give you 0. So when I look at the value 0, I will find that my substitution got me 0 also. And then substitute the upper limit for your variable 1, because y works from 0 to 1. So if you substitute the 3y squared, put y equal 1, you get 3. So at 1 here, you can find that I graphed it at the value equal to 3. And link the 2 points by a curve, like here, you link them by a curve because your function is 3y squared. Y squared is a curve, so you graph it by your hand by a smooth curve. But if it's y power 1 in any graph, you can graph it by linking the points by a ruler as a straight line. Now, if you go to the second part, which we need to graph the capital F, you can see that our large curly bracket has three values, 0, y cube, and 1, and each of them corresponds to a specific range of y. So if your y before 0 in this area, you can see that your capital F has to be 0. So he graphed the horizontal line black or bold on the same line. And in the middle, you have y cube. Again, in order to graph it like the one before, substitute y cube, replace y by 0. It will give you 0. So at 0, we graph a 0 here and substitute the upper limit or the maximum value of y, 1. If you substitute 1, you get 1 cube. You get at 1 here the value also 1. Then link the 2 points with a curve between these 2 points. In order to complete the graph, you have the third branch if your y is greater than 1. So for any values greater than 1, like here, your value of f always 1, so he graphed it like a horizontal constant line with a height starting at 1 and continue up to there is no limit. This is how we graph the small f and the capital F. Now, if we go to calculate the probability in the second requirement, he asks us to calculate the probability that y between half and 1. We can get it using two techniques as he asks. If you look down here, you can see that the probability that y between 0 and 1, ignore that there is an equal sign or not, because we said equal does not make any difference in the continuous case. If you write y between half and 1 equal here or there is no equal, all of them are the same. You just have to integrate from the first point, which is half, up to the last point, which is 1, the function he gave you, which is the dynasty function he gave you as here. And this is a simple integration, y cubed over 3, and you multiply by 3 because it was 3y squared. So you get y cubed, then you substitute by the y cubed by 1, minus you substitute by half, you will get a final answer as 7 over 8. You can do it using a different technique by looking at the function itself, which is if you need a probability that your y between 0 and 1, my capital F, which is the very large curly bracket above we obtained, calculate the probability that y less than or equal a value. So if you imagine that I need the probability from half, if this is the point half, which is 0.5, here the 0.5, I'm trying to write 0.5 with this marker, and up to 1. So we need the probability from 0 up to 1. I can imagine that the capital F, if I put a capital F here of 1, it will give me the total probability from 1 up to the starting point. So it will give me from 1 down up to the beginning. And if I get the capital F at 0.5, it will get me from here up to the beginning. So the difference between these two, between when I get at 1 and when I get at 0.5, the difference is the area between 0.5 and 1, which is the shaded area, which what I need. As you see here, all what you have to do, get the capital F at 1 by substituting in the middle part by 1, you get 1 cube, and substitute again in the middle part by 0.5, you get 0.5 cube, then subtract, you will get the final answer as 7/8 as the one you got before, which is the same answer. This is another example that he gave us again the dynasty function for a random variable y, which works from between 0 and 1. And he asks you to get the c value, so you integrate and equate the integration with 0. He asks you to get the capital F as we did before. We can do the very large curly bracket. He asks you to graph both. We can do it, and you will see all these solution or solve it in next slide. He can ask you here to, when you get the capital F, to substitute whatever using -1 or 0 or 1 to get the capital F value. And this is just a wording question. He is saying in number 5, find the probability that that a randomly selected student will finish in less than half an hour. So all what you have to do to get the probability that your y works. So here, probability that my y is here y less than, you write equal or not 0.5 or a half. So this one, in order to get a probability that your y is less than half, all what you have to do to integrate the function, which is here between 0 and 1, you integrate from 0 up to half, as you will see in the next slide. The last requirement, which is number 6, is a bit important one, because he's saying, look at the first word, given that. So it's a conditional probability. Given that this is a given piece of information, that suppose that your y is at least 15. Your y is at least greater than or equal 15, at least 15. Then he asks you to find the probability that she or he will require at least 30 minutes. So given that your y is greater than 15, so this one you write it after the given, so it's like we write like this, the probability. Here, the first word he gave us that our y, so we will write like y is greater than 15. So here my y is greater than 15. And this is given that, so I will put it after a given mark, after the conditional probability mark. Then we need our y to be greater than, because he said at least 30, so at least greater than 30. Again, you write equal or not, it won't make any difference. And if you remember, this probability has to be translated into intersection between y greater than 30 and or intersection y greater than 15, over the one closer to the equal sign, which is the probability y greater than 15, as we'll see in our next slide. Here you can see the solution of number 1, which we integrate the function fully over the interval from 0 to 1. We integrate the function fully from 0 to 1 and equate the integration with 1 in order to get c. We got c here equal 3 over 2. And in number 2, we need to get the curly f, but here he got it only the middle branch, because in the first branch, as you remember, if our y before 0, we get 0. If our y is greater than 1, we get 1. But in the middle, we integrate the function given, which is, as we said, c is 3 over 2y squared plus y. So we get this value as the integration if our y in the middle. So here, this one is exactly like the big curly bracket, but we ignore the first. You are not supposed to do this. If you are answering in an exam sheet, you have to write the 3 branches. The first one, y before 0, and you write 0. The last branch, if my y is greater than 1 and you get 1, the middle branch, you integrate the function I gave you and you get the answer as I show you here. But for the sake of space, we did only the middle branch. And if you see in number 3, we graph the function as a curve by substituting the 0 and the 1, and we graph in a form of a curve by hand. In number 4, we took the solution we did in number 2, and we need to get f of minus 1. Minus 1 is before the range you see in number 2. So the answer is 0 because there was no probability. And f of 0 is that you can take it from the branch we get in 2 by substituting the y cubed over 2 and y squared over 2 by 0. You get also a 0 here as a solution as you see before you. And f of 1 you can substitute in the same branch we got in solution number 2 here by 1. So you get a 1 as you see before you. Now, for number 5, if you need a probability that y less than half, all what you do, substitute in your second answer, in answer number 2, half in the replacing the y by half, you get the answer as 3 over 16. Or you can do it without the capital F by going back to the original function. And if you need a probability that y less than half, you integrate from 0 to half over the function I gave you to get the same solution. The most important requirement was number 6 because it's a bit weird. As we said, the translation, it would be the probability like this one as required like this one. I think here there may be a mistake that he wrote y greater than 0.25 and y greater than 0.5 given that y greater than 0.25. If you remember in the previous requirement, he said that it's no, there is no mistake because he translated the minutes into like a part of an hour. If you remember, he said, given that the students need at least 15 minutes, so 15 is a quarter of an hour. So he wrote it, if y is greater than 0.25, then he need the probability that at least 30, which is half an hour. So it's here. I'm just got confused because I'm looking at the slide before me. I don't have access to the slide before. So as we said, in order to do this, you have to write first that it's an intersection between the two events, y greater than 0.5 and y greater than 0.25. And the intersection will be this part in the numerator, which is greater than 0.25. And divided by the one closer to the equal sign, which is this part divided by the probability y greater than 0.25. In order to get the numerator and the denominator, all what you have to do, substitute in your capital F, which we obtained in 2. But remember, in your numerator, we need the probability greater than, and your capital F get you the probability less than. So 1 minus the probability less than 0.5, which is 1 minus the capital F at 0.5. The same can be done in your denominator. You need the probability greater than 0.25, which is 1 minus the probability less than 0.25, or 1 minus the capital F at 0.25. Then we get the answer finally as 104 over 123 here. Here are two exercises that you can solve just like the same previous examples we did before, and given to you as here the answers inside red rectangles, so that you can check your answer if it's correct or there is something you need to ask about it. Here I just summarized in a table the comparison which we did in the beginning of this part between the discrete random variable and the continuous random variable in terms of its values. The values, this one can take which jump 0.0123, and here it's like an interval, and also this one can work the probability distribution as a table if we like to put it in a table or a graph or a formula like the binomial. But here, since it works like an interval, any required probability has to be an area under a curve, and we have to obtain it like integration. In the table, if you look here, the total probability is 1 by summing the probabilities. In here, the total probability is 1 by integrating under the whole dynasty function so that you get 1. The expectation, as we'll study in our next part, in the table you multiply y by the probability of y, then you sum, you get an expectation or mu or average. Here we will have to integrate, we don't sum, we integrate y multiplied by the probability of y or the density of y, integrated over the whole range of y's you have, you get the expectation. We also saw how to get the distribution function in the discrete case and in the continuous case. And we can say the same if we talk about the moment generating function later on in our second part, which I will explain shortly in another few slides. Here, as you remember, the definition of the MGF is starting by summing ETY-PY. Here, the definition, there is no sum. It has to be integration EY multiplied by the density function f of y dy. This is like a table summarize all what we have to say as a difference between discrete and continuous, so that you remember